So let me share my screen.
Yes, sir. Yes, sir.
Yes. So is my screen visible?
Yes, sir.
Okay. So thank you all for inviting me. And since Haldia is my own college, and so I had a good association with Haldia, HIT, being a student of HIT, and later on being a faculty of HIT. I am really happy to again come back to this platform to share my research on and also ongoing research on particularly on object tracking and object detection, video object detection and tracking, mainly with the for visual surveillance applications. Okay, so as Madam has already pointed out that I have been working in domains like object tracking, image segmentation, intelligent transportation systems, augmented reality, virtual reality. Most of these domains actually require the knowledge of machine learning and deep learning, and particularly the concepts of object detection and object tracking. So today, I shall be showing you some of the latest research work being carried out at various institutes and what is actually going on into the domain. So we can have discussions maybe toward the end of the session. I shall be happy to listen from you, your opinions, and I shall be happy to discuss with you. If you have any queries in between, you can also ask me. That's not an issue. So let us try to understand that what are the challenges related to visual surveillance. So if you take this image, you can ask hundreds of questions from this image, out of this image. You can ask a question like, what kind of scene it is? Or the next question can be, where are the cars? You can have another one question like, how far is the building? So these are the three questions. But actually, you can formulate such. I think there is some background noise coming. Can the moderator please check that?
Hello, all of you. Please put off your microphone, switch off. The sound's disturbing a lot. Sir, please carry on.
Okay, thank you. So, like question like how far is the building? These are the three questions I am just asking. You can ask actually hundreds of questions from the same image. Now, we humans, we can answer some of these questions, or probably we can answer all of these questions depending on what knowledge we have. But let's assume that a human can answer all these questions which can be asked about the particular image. Now, if we want a computer to answer these questions without the help of a human, then you need to make the computer intelligent. Okay. So that is what our objective is. The computer vision research community, what they are trying to do is to make the computer intelligent by infusing intelligence into the computer so that they can answer these questions. Okay. Even you don't assume that all the computers will be answering in the same way. Like if you ask the three questions on the right side to 5 human beings, they may also answer differently. Okay. So it's not like that whether they are answering differently or not. The question is whether they are able to answer it or not. A particular question, what kind of scene, may have multiple answers also. It's perspective. I may tell that this is a natural scene. Somebody may say that this is a parking lot scene. Somebody may say that this is a scene with And some of these applications like Google Cars, these applications are not new. They are maybe 10 years old, but still they are not fine-tuned enough so that they can be commercially used. I know that there are pilot studies going on, but if you want an autonomous vehicle to run freely on roads or every segment of the road, it's probably we are 50 years behind. We need more time before a car can run automatically without the help of a driver on the roads of Kolkata or maybe in Haldia or anywhere on the earth, unless you specifically mention that this road will be only used by autonomous vehicles. There will be no cattle, there will be no humans, there will be no other vehicles. So, but that's not a natural scenario. Natural scenario means you are free to move. Okay. So the technology is evolving, but it will take time. Because vision is a challenging problem, that's why we are not able to come up with a full-scale solution yet. Okay. You may agree with me or you may disagree with me, but the point is, in my opinion, it will take a long time before we can realize that car is autonomously driving and taking you to the airport from your place, unless you are staying in a city where probably all roads are open, there is no cars, something like that. But that's not the normal scenario. Okay, so that's why it is challenging, and I'm also optimistic. I'm not pessimistically saying, but I'm saying that it will take time for such solutions to come. Being a computer vision scientist for last 15, 20 years, I know that how difficult it will be. Now, to develop such systems, we need to make the machine intelligent. And for making the machine intelligent, we need to make the machine to learn. Okay. Now, how do we define the learning? And how do we basically ensure that the machine learns? So we want to develop algorithms that allow computers to learn. In this particular talk today, or in this course, or FDP, we can assume that it's a narrow definition we can assume. Like learn to assign an object or an example to one of the several pre-classified categories. This category can be anything. It can be a bus, it can be a human being, it can be a car, it can be any other object which you see. So the problem is actually a pattern recognition problem. Now let's see an example. Say if a face photograph is given like this, okay. So we do not know that whether it is a face or not. And you ask questions like whether it's a multiple choice question, whether it's a teacup, whether it's a face, whether it's a phone. When your computer can answer this, that means the computer has learned about the features of this object. And then the computer suggests that it's probably a face. And if you go to a further advanced level learning, then the computer can even say that probably this is Bill Gates' face. So that's what we talk about when we talk about learning. Now, so we initialized the talk on detection and learning, and then let's see that how when we talk about objects who are moving. So objects which are moving, that we need to detect those objects in each and every frame so that we can track them. Now, finding how objects move in image sequences or videos, it can be in three-dimensional space, like an aircraft is moving or flying, or movement in image plane. Also, you capture the video of the aircraft moving, but when you see it on a computer screen, you see it's in image plane, it's moving. Okay, so it's 2D. Now, what are the camera options while you capture those things? Your camera can be static camera, it's fixed, doesn't change, where the objects are moving. The second one is the camera is moving and objects are moving. You know, it's going to be more difficult. This camera is moving, object is moving, theory of relativity comes, you know, Einstein's theory. So even the algorithm will be confused whether the object is moving, because if the algorithm doesn't know that the camera is moving, then the algorithm may be confused. So that's why it's really challenging. The second part is more challenging when moving camera and moving objects. We'll see that some of these applications. Now, a typical object tracking framework looks like this. In the start, you localize the object and you follow the object. And this is a loop basically. You follow the object in successive frames, and when your following is done, then you end it. So you get the trajectory. So it's basically the tracking framework. Now, localization of the object, it requires the knowledge of machine learning and deep learning. Okay. Following of the object can be done in many ways. You can actually apply the physics-based rules also, that if the object is moving in this direction with this velocity, then its position in the next frame will be here, because you know that the rule of physics will work. Also, you can do the other way. You localize the object in each and every frame, and then you try to associate them. Okay. So you can directly apply machine learning on each and every frame, and then detect the objects and try to associate them. We'll see both the examples, how it looks like. Now, localization of objects. Okay. It's basically helpful in finding a target object to follow. Now, if you are following an aircraft like fighter jet, which is moving very quickly and with doing difficult maneuvers, you know that following that object will be difficult because that's moving very fast also. Easier maneuvers can be like the aircraft is moving on tarmac, or maybe just trying to reach to the runway, or maybe an aircraft which is a civilian aircraft which is running at a high speed, which is flying at a constant speed without doing difficult maneuvers. Those are easier conditions. Okay. How we can do it? Localize the objects. You can localize the objects by frame differencing, moving edge detection. You can also apply AI/ML based object recognition techniques. Okay, yeah, the frame difference techniques, like I have given an example here. Basically, if you have the ith frame and you have the I plus 1th frame, you just do the differencing, you get the difference image, and you see that what are the changes. This is a very simplistic approach, which may not be always giving good results, because it's difficult to, because this frame difference itself, these images are also noisy. Often the difference may not lead to some good visual observations in the difference image. So that's why it may be difficult. So there are challenges. So estimating the true difference requires accurate background information, which may not be available with you. If the lighting changes over time, what to do? If the camera moves, like I was talking about, if the objects move very fast, if there is occlusion, background clutter, and also there are other environmental conditions which may vary depending on situation to situation, and the problem can be highly challenging. Okay. Now, background modeling, if you look into the preliminary way of doing background modeling, you basically do periodically modify the background, whole background. Okay, it will also include the changes in the new background. So it systematically incorporates non-changed portions of the image into the background. So if assume that if you have LIT is the background, then BIT will be BIT minus 1 plus LIT. So if you have else, otherwise BIT will be BIT minus 1. So if you get some new background at the ith frame, you basically add it with the previous frame. But there are issues. It is easy to identify changes in image data, but what does this change mean? Do you really get any meaning of this change? Okay. So it needs a second layer of processing to recognize the changes. What are these changes? Whether a new object comes, and if it comes, what is the new object? So that's why it is really challenging. And then you need to also target or object follow. You need to follow them. Okay. So observing the positions of an object or objects in a time sequence of images. That's basically object following. So how do we do it? We match the objects in each frame. We found minimum path curvature. We do model-based paths. We do prediction-based methods also. Let's take this example. So at frame I or frame 1, the positions of the objects are like top two circles. This one and this one. This one and this one. Okay. Now, in the next frame, the connections can be like this. The paths can be like this. But can I guarantee that the paths will be always like this? If these objects are similar in nature, we can have a path like this also. We can have a path like this also. These are only two set. I mean to say, these are only 2 points. If you have multiple points, you can understand that how many different combinations possible. And how do you know that? Which is the correct path? If these objects on the left side and right side, they are looking similar. Okay, so there are 2 white looking cars. Okay. Now anything can be correct. This one can be correct. This one can be correct. This one also can be correct. So the association itself is a challenging problem. Okay. And how do we associate? There are many methods. I'll show you some of those methods, how the association can be done, but it's really a challenging problem. Okay. So if you solve it with the rules of physics or with the rules of prediction techniques, or you apply some prediction techniques, okay. For example, the object which was moving in this direction suddenly changed the direction, changing the direction is highly unlikely. So possibly this object will move from here to here. So these sort of predictions can be done. But again, these predictions work in short range. It may also fail in some scenarios and longer range. Okay. So which is the best solution? One with the overall shortest path? Okay. How do you do it? For each solution, for each path, you compute total curvature. I mean to say that there's no definite answer, which I can tell that this is right and this will always lead to a correct answer. No, it's not possible. It varies from time to time. Okay. Then we have model-based tracking, where basically the mathematical models of the object's motions are done. You estimate the position, velocity. Velocity is basically you represent it in terms of speed and direction. Then acceleration, you can use it, and you can predict object's position. Okay. So you have a motion model. From the motion model, you predict the location, you verify the location, you update it. If you are satisfied with the verification, you update it, and then you can apply the motion model. Simple motion model can be a Newton's law. Like you know that st equals to s0 plus ut plus half at square. And you apply it. If you know the initial position s, you know the velocity, initial velocity u, so probably you will be estimating that what will be the velocity at time t. So that's what we do it, if I know the acceleration. Okay. Now, we can predict position at time t, knowing position, velocity, and acceleration at t equals to 0. Now, I will show you some of the applications of this tracking in a dense crowd scenarios now. Okay, where we have applied not this velocity or position or acceleration, rather we computed energy and entropy. So we computed kinetic energy and entropy and we applied them on dense crowd scenarios. Okay, so let's take this example, which is a dense crowd scenario where it's a marathon scene. Okay, we actually applied Gibbs entropy. I'm not going to the formulation of all these things. Okay, and when we applied Gibbs entropy, we found that the entropy is almost constant, even though it's a little higher, and energy is lower, but there are some fluctuations in the energy. This is one type of crowd. And when we see it for a different type of crowd, like Puri Rath Yatra crowd, we see that entropy is high, but entropy is basically fluctuating. These are all based on our velocity estimation and position estimations. So, and they are of two different crowds. So what we can observe that if a significant fluctuations are observed in interframe energy, it can be attributed to a fast moving crowd with higher velocity. That is what we can conclude it. And if the fluctuations in interframe energy difference are low, then the crowd can be assumed to be moving at a uniform but lesser velocity. And similarly, more fluctuations in the entropy curve indicate varying randomness. These are all empirical observations. So based on these empirical observations, we can actually define certain rules. And that is what basically we have done it here. Now, for tracking, you can actually extend it further. That is what actually I would like to show you, how tracking can be done, particularly in dense scenarios where the particles are moving in a dense environment, like political rallies, festivals, which are very common in our country, and they are needed to be tracked for safety reasons. Okay. What we tried to do, we tried to apply the rule of physics, mainly for Brownian particles. With the help of Langevin force model, we tried to understand that whether the same can be applied on the crowd movement or not, obviously with certain relaxations. Okay. So it is, if you look into if you go to the background, okay. So we found that it is perhaps the simplest way to describe the dynamics of a non-equilibrium system. Okay. And if you look into the right side of the image, by a Brownian particle, let's assume that this is a particle, or this is a human being in a dense crowd. What are the different types of forces being applied on that particular particle? You see, there are mainly three types of forces. One is random fluctuation force, this one. Then the Newtonian force, which is because of the particles which are around it. And then the friction force, because the object is moving. This random force is basically the noise. Random fluctuation force you can consider is a noise, system noise. Whereas this Newtonian force is basically it's a frictional force. Newtonian force is basically its attraction force. The nearby particles will attract. So why this force will be there in a following model? So if this P particle will be attracted toward the other particles who are moving in the same direction, by this corollary, you can assume that this is a Newtonian force. Then frictional force, because particle has an objective to reach to a destination, it will be going through this dense scenario, it will be experiencing certain frictional force. So that's why, okay, this is, formulated like this. Now with the equilibrium system, non-equilibrium system is dynamics of the non-equilibrium system is given like this, where gamma t is the frictional coefficient and zeta t is the random force arises due to the random density fluctuations in the fluid. Now, what we can do it with this force model, so we have three components. One is external force, one is drift, and one is disturbance. Disturbance we have already looked into. This is the disturbance, random fluctuation. Then drift is confinement, that within an area, and external force is basically the objective where you are going to what direction. Okay. So the same can be actually formulated, and you can estimate the position of the particle in the next instance. Okay. So with this force model, you can define the movement of this group of pixels. Okay. And understand that what will be their positions in the next frame. And this has already been published from our research lab in Expert Systems Journal, Expert Systems with Applications. We have shown that with this kind of flow modeling, we can actually estimate the flow correctly, particularly in dense scenarios. Okay, so this is the entire framework where we put the image frames and we estimate the optical flows and then do the processing. So you have a video sequence. We define temporal window frames. So say W number of frames are in a temporal window, when we process that whole set of frames and we do the linear dominant flow segmentation over the window. So we would like to estimate the dominant linear flow. This particular model doesn't work for nonlinear because this is passive Langevin model. This passive Langevin model cannot handle nonlinear flows. That's why it's purely linear dominant flow segmentation. Okay. Now, once you do this tracking, how this, a typical tracking and application framework can be used, and what are the applications? That is what basically we will see. So let's assume that you have done the tracking. A framework looks like this. You have a CCTV camera attached where you extract the key points, you track the objects. Multi-object tracking means you track multiple objects. You extract the trajectory and you create a database of the trajectory. So trajectory means you record the position of the object in each and every frame. You record the position of the object in each and every frame. That is what basically you are doing. And from this trajectory database, you can extract various types of features. We'll see that what kind of features can be extracted. And then you can apply it in various situations. Like you understand that you would like to understand that based on the object movement, which are the interesting regions in a scene, or what kind of movement is abnormal movement, or what kind of movement is normal movement. And you also do some kind of high-level applications like, synopsis generation or summarization. Okay, I'll show you some of the examples of this one. But before that, let me explain that what do we mean by tracking, or how do we represent rather tracking? So tracking is to localize objects in continuous video frames that we have already seen. Now, how the trajectories are defined? Trajectories are usually defined using these triplets. You have X, Y. I'm talking about in two-dimensional representation. X, Y, and its time. Okay. So with the X, Y coordinate, you know that position, and time, you know that what is the time. So at every point, you can know that where is the object. At every time, you know that where is the object. Now, when these object tracks are represented in 2D vis-a-vis 3D, you will see that there are certain advantages of representing in 3D. For example, in the 2D scene, if you look into the left side, an object has moved from this location to this location. Now, you don't know that whether the object from this trajectory, if I only give you this trajectory, you can't comment anything about that, what was the behavior of the person during this movement, because you don't have the time information available. Whereas if you represent it in 3D kind of thing, it gives some information that probably the object was moving in this direction and it spent some time without changing its location at a particular point. So during these frames, the object was static, and then again it started moving. So that is one interesting observation. So with a projection like this, you can probably say that this is the area where possibility is there the object was staying for some time, so it may be something interesting location. This is just an observation. Now, if you basically apply tracking, then tracking is also challenging in many cases. For example, if you get these tracks very, short duration tracks, I hope the video is playing on the other side. Can someone confirm that whether the video is playing or not?
Yes, sir, it is playing.
Okay. So you see that we are getting small tracks. They cannot be useful actually. You don't get any conclusion from these tracks. So rather, this is basically output of KL tracker. We would like to see that whether the tracking can be done for long duration or not. So this is one of the outputs where you can see that this will be probably more useful for doing post-processing, the application post-processing, where you track the person for longer duration, even when the person is going through multiple persons for longer duration, you can actually track. And this trajectory will be probably more meaningful than the short duration trajectories. Okay, so if we are able to extract the trajectories for each and every human being who are currently in the scene, then probably we can do post-processing. All the applications, like try to understand how many people are entering, how many people are exiting, how many people are currently staying, where actually they are leading to, through which gate they are entering, through which gate they are exiting. All these applications can be developed. Okay. So long duration tracking is really important. Now, obviously, if you do long duration tracking, you may not always get a scenario like the previous case. You may get challenging scenarios like this one. Like this is one video we recorded from the top of our School of Electrical Sciences building on a rainy day. You can see that the situation is not good. I mean to say that the environmental condition was really noisy, and we applied tracking of the objects using some algorithms. Obviously, our refined algorithm is there. It was able to track even those objects in a rainy condition when when there was occlusions like those trees. How it is possible? Obviously, we modified the algorithms. Okay, predicted the positions using Kalman filter-based prediction, and it helped us. So why I'm showing this one? Because this is a challenging scenario. Okay. Similarly, if you look into this, sometimes this also fails. Even it was tracking the person. Even it was tracking you see the interesting thing, it is maintaining the level of the object. 74, 77, it is being maintained. So that's an interesting part. Maintaining the object level is basically the tracking. Okay, so that's one. Now this is an easy scenario where tracking is possibly very easily done. Okay, but you don't get always such scenarios in real life situations. Okay, like this is one where tracking is more easier because you know that the objects are clearly visible and you can maintain their tracks for long duration things. Okay. Whatever I have talked about tracking so far is based on models, either motion models or prediction models. We did not apply any kind of detection. Now let us see that how deep learning can actually help this. YOLO architecture is a very common architecture for object detection. I'm not going into the details of YOLO architecture because this is well known. This architecture is very common, and it is highly successful in detecting objects. It has several layers. These layers actually perform convolutions with different types of filters and essentially, map them to the fully connected levels. Okay. Now, with this, when we applied for detection, I will first show you the detection result. These are not tracking results. How accurately the detection can be done. Just look into the video output. You will find that how accurately it is doing the detection. So you can see that when the person is coming, it's not tracking, it's detecting. So even handbags are being detected. Person is detecting, handbags are being detected. The quality of image of the handbags were definitely not good, but still it was able to detect. Like this student, she was even speaking over phone. At some point of time, cell phone came. So that is why, though it looks like tracking, but it's not tracking. It's only showing person. Whether it is the same person or not, that we are not claiming here. That we will do at later stage. So this is basically detection results. You see the more results, person detection from a different camera. We actually set up different cameras at multiple buildings in our department and tried to understand that whether the detection was working with good accuracy or not. Even it was tracking, detecting objects which were far away from the camera. Now, with the help of a framework which is popularly known as simple online deep tracking, SODT, we can apply tracking. Now, how does, let's understand this framework. You have the video, and the video gives you the frame I as well as frame I+1. You apply object detection using YOLO in both the frames. So the first step is detection, and it detects the objects here, couple of objects on the top frame, couple of objects in the bottom frame. And then this paper actually proposes an association based on appearance cost. So the appearance of these objects are matched based on some associations, feature-based association, and then they try to match them. So once they do it, they find that this particular portion, which is taken from here, is matching with this particular portion, which is taken from here. So that's why they are doing the association here. Similarly, the association for the other person is done like this. So this is called deep association and tracking. Okay. Now, when this has been applied, here you see the tracking. You see the number on top of the window. That's the reference. So that means you are tracking the person. You can see when it goes far away, it was because it was detection based. And in between, it actually went inside the, it was occluded partially, so it could not recognize it, that whether it was the old object or new object, because it was not doing any kind of prediction, path-based prediction. That's why the level changed. But for a larger amount of time, it was able to maintain the levels. And when we applied it on multi-object tracking, objects of similar type, it was also working. We can see that 17 level, it was initially missed, then now it is maintaining 20. Even though there was a false tracking initially, but now it is maintaining the levels. So this is what the multiple object tracking or multi-object tracking. So tracking multiple persons. Another example you can see. So these videos we have actually data set we have created, and we tested the SODT framework, and we found that this is working fine, reasonably good. When we tested on public data sets also, you can see largely it was able to maintain the levels. These numbers it was able to maintain. Even though here and there are some false positives or false negatives, but largely it is fine. it is working fine, even though the density, crowd density is sparse. Okay, I know that the crowd density is sparse, but it was able to track. So I'm showing results on different conditions so that you get to know that what are the varying conditions we can encounter in real life surveillance scenarios. Okay, so this is another one where you can see that the tracking is done with considerably good accuracy. Even when these people will be mixing up with each others, more or less they can maintain the levels. Okay, so that's an interesting part. They are maintaining the level, like 849. I know that in some cases they are missing, but 84 is still that 8 and 4 they are coming. 9, 8, 4, 9 they are coming. So that's one thing. You know, it's interesting that the algorithm is able to track for a significant amount of time, even though the scenario is really confusing because these people are grouped together, they are very close to each others, there are lots of occlusions. Okay, so at least the object number 8, it is being tracked properly for long duration. Now, so far what I was talking about, the supervised tracking. I mean to say that you use deep learning framework to detect object and then associate these objects across multiple frames. So that requires, if you want to train the framework, you need labeled data. That's why it's supervised learning. Now I shall show you some examples of unsupervised learning also. Here, I shall give you a brief overview that why we went to the unsupervised tracking. There are some reasons for that. So Dirichlet process, which was proposed in 70s, that process led to various kinds of modeling, particularly for understanding behavior of dynamical systems. Okay, so it has been used, and we actually found that with the help of Dirichlet process, we can estimate the variable length temporal analysis of motives. Okay, so this motion which are happening in short durations and the spatiotemporal representations of the motions in terms of motives. And one of the frameworks which has been published by Santosh et al., he did PhD with me. It was a Bayesian framework-based probabilistic model to predict the position of or to group the pixels in spatial domain, as well as connecting these pixels in spatial domain, which are grouped in spatial domain across multiple frames with the help of this probabilistic Bayesian model. Okay, which is a topic-based modeling. So we give the name as the original proposal was Dirichlet process mixture model. So we actually modified this one. We call it MDPMM, and this MDPMM was able to track these objects very accurately. So this has been published in IEEE Transactions on Intelligent Transportation Systems. Those people who are interested, they can look into the paper, the base paper. It's a little bit mathematical modeling, but this is an interesting one. And when we actually compared the tracking with respect to the existing algorithms like KLT and mean shift, which are mainly unsupervised tracking, okay, we found that temporally unknown incremental clustering based MDPMM, TUIC based MDPMM is performing better as compared to the other unsupervised tracking algorithms. Now, once we track these objects, how can we use these tracks for some applications? I shall show you some realistic applications of tracking and detection and tracking, which will be used for visual synopsis. Now, this is a scenario which I am showing. It has been recorded from top of the building of one of the residential areas at IIT Bhubaneswar, and he recorded the trajectories of various moving objects during 1 hour. So what do we mean by synopsis? Let me first explain you what do we mean by synopsis. Synopsis is something like that. You have been given a 24 hours video or maybe 6 hours video. Okay. And if I ask you, you generate the highlight. So that's basically synopsis. So you do not want the synopsis to be very long. You do not want the synopsis to be confusing. You want rather the synopsis to be easy and you can get meaningful information. So you do not want to, like sports highlight, you don't have enough time, 7 hours time to see the whole cricket match. Rather, you want to see only maybe the 5-minute highlights or 10 minutes highlight or maybe half an hour highlights, just based on your choice. Now, whatever the highlights that currently these channels are providing, you may not be satisfied with the highlight. What you want? No, I want to generate my own highlight based on my own choice. Say yesterday there was a cricket match and you missed the cricket match and you want to see only the actions while a particular player was doing something. So how can an algorithm can intelligently generate that synopsis? That is what I shall show you. So this work has been done by one of my students, Arif, who was also with HIT. Many of you definitely knowing him, Arif. He did this work in his PhD while he was working with me. So what he did, he basically analyzed this track and tried to understand the behavior of the objects, and based on the object nature and behavior, in terms of trajectories, he generated the synopsis. Synopsis means summarization. Let me show you an interesting result of the work that Arif actually carried out. The original video was 1 hour video. The original video was 1 hour video, recorded from morning 8 o'clock to 9 o'clock. Now, after all the processing, he identified that there are mainly 3 regions through which the objects are entering: the red region, the green region, the blue regions. And all the paths which we basically saw in the earlier diagram, these paths were like that. The possible paths can be, we are showing some of these paths, like entry is the blue. Then the vehicle or object can move from here to here, here to there. The entry is green. Object can move from here to there, here to there. Entry is red, this. Exit is blue, this and this. Exit is green, this and this. Then blue to green, blue to red, green to blue. You can also define others, like red to green, you can also define. So there are many possible ways, possible paths. I'm just showing some of these paths, but there are many other paths also. Now, I have been given this 1 hour video and it has been analyzed offline. Now I want to see the movement of the objects that happened during the 1 hour, where the object movements were only green to blue. Only green to blue. I do not want to see any movement other than green to blue. And this video will be automatically synthesized, generated from the master video. That's why it's synopsis generation. Remember, it's not that somebody is cutting and pasting manually. It's automatically generated video from the whole master video, which is of duration 1 hour. Okay, let us see what it's doing. So when the synopsis query was given green to blue, this is synthesized video. The background is static. All the moving objects are actually dynamically pasted on the background frame. That's why you can see some of the false positive cases like 9, 12. And what are the numbers? These numbers are actually when these vehicles actually move. So if you look into why I'm saying that this is interesting, now look into this. Okay, now look into this. So the time, let me advance it a little bit more. Look into this. The vehicle which is coming at 9:2, or the object which is coming, particularly these two. So the vehicle moved at 9:2. This person moved at 9:12. But both are being shown at the same time. It's not practically possible. Because the vehicle actually moved at 9:2. Whereas this person moved at 9:12. How they are appearing at the same time? That's because they are pasted over the background frame. Now, before pasting, you need to extract all those object trajectories. Not only trajectories, they are original, boundaries also. And we created the tubes. These are called tubes. Now we extracted all tubes for the entire 1 hour video, and we created the database, and then we did an optimization. That's a spatiotemporal optimization. Why it is spatiotemporal optimization? Because my spatial frame size is fixed. It is only this frame. So if there are 100 objects which are moving, I cannot put all of them because that will not create a soothing video. It will be a confusing video. One object will be over another object. And why it is temporal optimization? Because I want to squeeze the total time of the duration of the video. If you look into this, total duration of the output video is 1 minute 23 seconds. Now the input video was 1 hour. So I need to place all the moving object without any kind of creating confusion in such a condition that the duration of the video is also minimized and the locations of the objects are also meaningful. Meaningful means it's not like that one object is appearing over another object. That's why it's a spatiotemporal optimization. This paper has been published in IEEE Transactions on another paper, Intelligent Transportation Systems. Arif published it. It's an interesting work. You can look into the paper, which actually talks about, and it actually uses a deep learning framework to detect these objects. Humans, cars. We actually tested with only 3 types of objects: humans, cars, and 2-wheelers. So it will show all 3 types of objects. And the entire video, synopsis video, it only shows the objects which are moving from green to blue. It will not show you any object which is going in other directions. And this video is synthetically generated. It's not like that we have cut some frames and pasted. You can see that all this, because these objects are pasted, there are blurring effects around these objects. So these are basically blending. So we applied, like this car suddenly appeared. There are some issues also. I'm not saying that this is 100% soothing, but it only shows you the object movements which are from green region to blue region. There are some abruptly some objects appearing and disappearing. These are noises. But mostly, this will show you the objects which are moving from green region to blue region. Now it has many applications. You think about a security situation where at the end of the day, the administrator wants to see all the vehicles that are of color red moved from point location 1 to point location 2. And it will be able to generate a synopsis intelligently, which is definitely not going to be 1 hour synopsis, because I don't have 1 hour time. I want to see only the gist of the video in 5 minutes time, or maybe less than 5 minutes time. So that's why it is spatial optimization, because you have many objects moved during the 24 hours. You need to place them properly. It's temporal optimization because you want to shorten the duration of the video. That's why it is called spatiotemporal optimization. Okay. So this is an interesting application of object detection and tracking. Then tracking for traffic applications. Let's see some of the traffic applications. The traffic applications can be like this. So you have been given the trajectories of vehicles or objects, moving objects, humans, okay. And you want to understand the dynamics of this traffic movement. So in this particular work, what I am showing you, how these trajectories, now we are not interested about the scene. We are rather interested about these trajectories. We don't want to identify whether this is road or whether this is car or something like that. The input to the system is only the tracks, because we have already detected those tracks using tracking algorithms. Now the data to the machine learning system, it is tracks, set of tracks. And with the help of this set of tracks, we would like to understand the dynamics of the scene. That is what basically I am showing you. So if what it shows, that these are all spatiotemporal clusters. All these cluster 7, cluster 10, cluster 12, they are spatiotemporal clusters. What do we mean by spatiotemporal clusters? It means that these changing colors represent that how much time actually it takes usually for a car to complete this particular motion type. It's not only all vehicles, it's basically movement type. Like for example, if you see the color is changing from pink to red here. Here actually pink to red in this direction. So all the possible movement directions are clustered and they are spatiotemporal clusters. On the left side, if you look into this, these are the original tracks, all the tracks. Then we are clustered tracks. And when we presented these clustered tracks on separate clusters, you can see this is one cluster, cluster number 10. This is cluster number 9. This is cluster number 3. Now, you can say that what is interesting? Interesting here is that the color gradient changes. This one actually provides the temporal information. With this temporal clustering, you can assume that how much time on an average the vehicles take to move this traffic junction. Maybe this time varies depending on the hour. So at 10 o'clock in the morning, it may be taking more time because the traffic was high due to office hours, or at 5 o'clock due to, again, the ending of the office hours. But other time, you may get a different type of scenarios. That's what is done. So how it can be helpful? Let's take the same example where I was showing you the tracking of a person in a long duration. The actual data set contains more than 50,000 trajectories. And if you put all the trajectory, it looks like that. It doesn't make much sense actually. Now, when we applied this spatiotemporal clustering, okay, and with the help of a very complex model, we call it TIGM, Temporal Incrementally Gravitational Model. With the help of TIGM, again, it's based on Dirichlet process mixture model, we were able to identify the prominent paths in the whole scene. And these prominent paths, based on its density and based on its intensity, it can actually tell you that how many people have actually traveled from this location to that location and what was their usual average time. So that how it is helpful. Now this will be helpful for identifying the pattern of movement in a busy railway station, which can be helpful to schedule the trains. Based on the movement patterns of the users, you observe it for first 5 days. Then you build this model, and then you say that, okay, my observation is that. So all these clusters, cluster number 26, they are not only spatial clusters. Remember, don't get confused that they are spatial clusters. No, they are spatiotemporal clusters. Okay, so the time is also associated. This work has been actually published in IEEE Transactions on cybernetics very recently. You can look into the paper. This is done by one of my PhD scholars, Santosh KK. So he published this work, and you can actually look into this. I'm not putting all the mathematics here because that will unnecessarily confuse the audience. But if you are interested, you can look into those papers. Okay. Now I shall show you another one application of this one. This is the current research work which we are doing it. That is basically hierarchical classification of accident-related anomalies, another application, particularly on road scenarios. What we are trying to do is basically trying to identify the behavior of the vehicles and the pedestrians and their interactions while they are on the roads. Okay, so in outdoor road events. Okay, so based on their interactions, what we are trying to do here is basically trying to detect car accidents, then vehicle hits pedestrians. We are also working toward solutions like illegal crossing of road, fighting on the road, all these things. So this part is already, the red part we have already completed, where we have applied deep learning frameworks to detect objects and to identify their interactions, and then find out that how the events can be detected. So one of the possible frameworks is like this. We get the input video like this. We detect the objects using YOLO object detection in these frames. We identify the interaction proposals, okay, body interaction proposals, and then we define positive back proposals, negative back proposals. We apply certain refinement algorithm, and then we apply classifier, mobile net classifier for extracting various types of features. And we basically do kind of heat map generation and then context analysis trying to do. So this is the overall framework, which is still, it has not been published yet. I'm just showing you the overall architecture because it has not been published yet. I'm not showing you the entire details, but this is the overall architecture which we have actually proposed it. And I will show you interesting results, how basically it gives. So you see that this is what we are able to generate. That means, you see, so prediction is this, the frame level heat map we have seen earlier. So prediction means you can see that everywhere we are detecting this, and then the heat map, and the final heat map we are showing it, and it also shows a description. What the description? It says that the start time of the accident in terms of frame numbers, obviously, at what frame number the accident started, how many objects are involved, the type of the objects, and possible area of accident. So that can actually lead to detect the severity of the accident based on the area. If you know that the large portion of the frame is affected, then you can use it as a metric to estimate that what is the severity of the accident. Okay, so this is what one example. You can see the other example where you see, and the final outputs are coming like this. So these descriptions are automatic descriptions. This can be helpful to the administrators to take quick decision that how these objects have moved and who are the objects who are involved into this. So that is what we have actually, we are able to do it. So for example, in this case, you can see that there are 4 objects, and even it detects that out of these 4 objects, 2 are car and 2 are motorcycles. These are automatically generated. And it shows that out of the entire frame, 20%, 19% of the entire area is affected. So based on this area, you can say that what is the severity. Again, this may not be correct that to decide that whether this severity can be detected based on area, but this is the kind of metric we are trying to propose. Okay. Again, you see that this also works in night condition. Okay, it's not like that we are not able to do it in challenging scenarios. Like in night condition, it is able to detect the accidents, localize the accident, then describe the accident with very good accuracy. Okay, even in night conditions also. So we tested on different data sets, and we found that the framework can be useful for detecting accidents and describing these accidents. Okay. All these videos have been taken from publicly available data sets. Okay. So with this, I shall finish today's talk. Let's have some discussions and Q&A session. So now I am ready to take up questions from all of you.
Thank you, sir, for such a wonderful talk. I hope the knowledge you imparted will definitely motivate the researcher of the field of AI and ML. Now, participants are requested to ask questions if they have any queries about the topic.
Hello, sir.
Yes.
Yeah. Thanks for the nice illustrations, sir. Very excellent illustrations.
Thank you.
One generic query at the towards end. You showed in the last slide some 19%. Is it including all the vehicles that are involved?
Yes, I mean to say that. See, this percentage calculation. Let me again show you. This percentage calculation has a little bit of heuristic that we have applied. I am not claiming that this is accurate. But what I am trying to say. Say possibly, let's take this example. So when it's showing 28%, so what we have tried to do, if you look into the heat map portion here, so heat map actually shows that if you look at the denser locations, I mean to say that where the intensity is high, that center location tells that where the impact. Okay, and if as you go away from the impact location, the intensity of the pixel changes. So we have used CAM mechanism. So there is a mechanism to understand the intensity, okay, of the feature. So this is based on features only. And we have used a kind of threshold that half, if the intensity drops down below half, then we will consider that pixel comes, I mean to say that above half, or half of the threshold, then we basically consider it is a part of the positive pixel. And then the negative pixel. And you have the entire frame size known by you, W into H. So based on that, we have calculated. That's what I'm saying. I'm not claiming that whether this gives a real measure, but it can be an indicative measure to tell that whether this can be used for, by the administrator to take a decision. Okay, now this accident involves 80% of the frame. So probably it is going to be a fatal accident. That's what I'm saying.
Okay, sir. Thank you, sir. And are you in discussion with any government agencies, because such a wonderful work, so that it benefits society, sir?
Yes, yes. Basically, this project is being executed with Korea Institute of Science and Technology, and we have also started discussing this one with Government of India, particularly for smart city surveillance. We have initiated a project at Bhubaneswar itself. That project, you will find the details of the project in my webpage. That's basically understanding the traffic behavior and anomalous conditions in smart cities. So I actually took up the example of Bhubaneswar, because Bhubaneswar is one of the smart cities declared by Government of India. It has recently been approved, and I have started the project. Maybe a couple of months back, we have started, doing the procurements and other things. It's a 3-year project starting from June 2021, and we have just initiated this.
Yeah, thank you, sir. Thanks for the nice session, sir.
Thank you.
Sir, one more questions in the message box. That is is it possible to analyze and cluster more than 2 frames of heat map, like the video frames?
Yes. Actually, you see, the frame level heat map is shown on the top right, whereas the below left is basically the consolidated heat map, okay, which is the heat map of the entire duration of the accident, because accident does not happen in 1 frame. The accident is happening across 10 frames. What I am showing, if I replay this slide, if you look into this, or say, you see, these are on the right side, top right, these are instantaneous heat map, okay. Whereas on the bottom left, it is the consolidated heat map accumulated over all the frames which are affected due to accident. Okay. Hopefully, this is what the question was.
Hello, sir.
Yes.
Devi, sir. In YouTube Live, Saurabh Mandal has put one question. Can your system be extended to calculate distance between 2 objects or vehicle which are moving? Currently, my students are working on social distance calculation, social distance among the person moving in a real-time video.
See, even I also need to do it. The challenges are in distance calculation. You need to calibrate the camera. The distance estimation will not be correct. It is possible if you basically calibrate the camera. So the calibration of the camera has to be done with respect to the scene. Okay. So if you know the intrinsic and extrinsic parameters, probably distance estimation will be can be done. But again, the problem is that with those parameters estimation, it's often the distance estimation is not correct due to the erroneous parameter estimation. Okay. So with camera calibration, you can do it like social distancing you are talking about. So let's assume that you have actually, let's take this example. Say, I'll not play the video. Let's say there is a camera which is recording this particular scene. Okay. Now, if this camera, this scene is recorded by a camera from a particular angle, if I change the angle of the camera, or if I put the camera a little bit higher altitude, what will happen? The scene will change. Now, the question is that the distance between the objects here currently, if you see, they will also vary. Now, if you would like to correctly estimate the distance in terms of meters, feet, or centimeters, you need accurate parameters. In a restricted environment, like inside indoor scenarios with lighting conditions not varying, probably the distance estimation will be easier. But in conditions like these outdoor scenarios with daylight changing, with night conditions, fog, rain, distance estimation may not be that accurate, but you can still do it. Some approximations can be done with camera calibration. That is what I can tell you.
Sir, may I ask a question?
Yes.
Sir, you are talking about the camera calibration. I want to ask you that whatever heat map you are giving, suppose I am using a thermographic camera. If I am using 2 thermographic camera on the same object, so can I take the 2 data set for a clustering one?
Yeah, if you have a thermal camera, see the thermal camera, they can be used for purposes. I mean to say that you can cluster the objects easily, because these thermal cameras are, highly useful. Okay, so they basically work based on the heat dissipated. Okay, So if you install thermal cameras, then probably you get better localization of the objects. There is no way, there is no doubt on it. Only thing is that
okay, sir, understood. If I use two cameras, two camera on the same object, in that case, is it possible to solve the problem that you were just explaining?
Yes. So that's basically the depth estimation solution. You have the disparity and the looking. So you basically create two images, okay, from two different positions. So you know that there is a disparity. From the disparity map, a simple triangulation will help you to estimate the depth of the object from the camera. Okay, so that's the standard geometry. You can apply that one. You can estimate the depth.
Thank you, sir.
Thank you, sir. Now I am request.
Hello.
Hello.
Joyita. There is a Prashant Joshi who raised a hand. If you have any question, he can ask to Devi sir. Prashant Joshi. Professor Prashant Joshi. No, I think probably he has left. Okay, Joyita, you can continue.
Okay, sir. Now I request Professor Tarun Kumar Ghosh for vote of thanks.
Thank you, Joyita. Am I audible?
Yes.
Yes, sir.
So good evening. I'm really glad to give vote of thanks on behalf of the Computer Science and Engineering Department, HIT, to my ex-colleague at HIT and today's speaker, Dr. Devi Prasad Dogra, who is presently an assistant professor in CSC at IIT Bhubaneswar. Whenever we have approached him for any kind of help, like delivering lecture in FDP, he has been always ready to help us. We are very much thankful to him for sparing his valuable time from his busiest schedule and sharing his important and interesting knowledge on deep learning for video object detection and tracking. Today we had an opportunity to hear his thoughts, and this will surely help many of us to take up the research and enhance existing research in computer vision and deep learning areas. Now let me present the certificate of appreciation to Dr. Dogra. Is it visible?
Yes, sir.
Thank you, sir. Thank you for your nice gesture.
Thank you, Dr. Dogra, for your valuable time and excellent talk. Now, finally, we want to extend our thanks to dear participants for patient hearing, despite a technical glitch at our end. Thank you all.
Thank you.
Thank you, Tarun Ghosh, sir. And thank you all the participants. Hope you will enjoy today's FDP. So hope you will join tomorrow, day 4 session from 5 p.m. Thank you, all of you. Good night.